Shri Gurubhyo Namaha Namaskaram. Shri Gurubhyo Namaha Namaskaram. So we are going to continue our discussions. Sorry. We are going to continue our discussions today on the concept of secure software engineering. So those who have not seen the earlier previous videos, please take a look at them. Okay. I'm now sharing the screen. Hope you're able to see the screen today. I mean the presentation deck. Okay, so we have been discussing about secure software engineering. So we will be continuing on that. So today our focus will be on the traditional software engineering deep dive. So before continuing, I just wanted to give a snapshot of what we have covered. So we have seen computer science fundamentals, okay, and then we moved on to the fundamentals of software engineering, where we talked about the basics of software, types of software, and a detailed analysis of the different programming languages, their generations, and the typical use cases, the pros and cons of that languages, etc. We had a detailed review of that. And then we moved on to what is called as software 3.0 as a focus, with the historical context of software 1.0, 2.0, and 3.0, and how the 3.0 is revolutionizing the software development in the agentic AI era. And we also saw how the benefits, the challenges around that, okay, and also the areas where we have to be cautious. And then we touched upon what would be software 4.0, or going forward, the future of software engineering. um, some thought process from reflecting what the subject matter experts keep saying. Okay, so all these links that we have covered so far is now part of a blog which we have, which I think some of you might have seen already. So wherein all the topics are given here, okay, including the recordings of the YouTube videos, okay, and a brief summary of the recordings, okay, and as well as the AI generated summary, okay, audio summary of that. Okay, so this is, for example, on the core concepts of computer science, and then topics related to fundamentals of software engineering. So there are multiple videos there, okay, part 1, part 2, etc. Okay, so and what they are covered here. Similarly, there are AI generated summaries of that, and this provides a mind map of the topics dealt here. So the different topics that we have been dealing with. Okay, so all that is being provided here. You can take a look at it. Okay, and then there is a 1 minute. I also wanted to. AI chat box where you can go and review it. Okay, so this is the agentic AI chat box where you can give your queries. Of course, you will not be seeing all these details. What you will be seeing is more in terms of how you will have access to that. So this is how you will be seeing the video, and when you click the chat, so the video, this is the details of the console. Okay, here you can ask your queries about the topic. Okay, so that this is what I have shared so far. Okay, and then there are the YouTube links. You can also directly go to the YouTube channel. So where all these videos are available for you to, I mean, take a look at your own pace. Okay, the recordings of all the previous sessions will be there, and whatever currently I am recording will also be posted here. Okay, so with this background, let us move to the next chapter. Those who have not taken a look at the earlier chapters, please take a look at it. Okay, and do subscribe to the channel so that you are updated with the whenever there's a new topic being discussed, you will be notified on the same. Okay, thanks for your support. So with this, we move on to the next topic. The topic here will be focusing more on the traditional software engineering process. Okay, to start with. Okay, so we will be understanding what is software engineering process, software engineering mind map. We will look at it, and the process governances around the software engineering. These are all the traditional ways of doing it. Why I am calling it traditional is that currently what we are doing it without agentic AI's involvement is what I tag it as traditional. I will also be covering how agentic AI is transforming these processes as part of the subsequent sessions. Okay. So, secure software engineering is a comprehensive methodology for creating software applications with intensive focus on protecting the sensitive data and preventing security branches. So, we saw about what is software, what is programming languages. Software engineering is the rigor in software production life cycle. Okay, so software lifecycle management, right? So it manages the entire rigor it brings in the engineering rigor for the software side. Okay, so the motivation for adopting this rigorous discipline extends far beyond technical best practices. They are deeply intertwined with core business and regulatory imperatives. It is business which drives these software engineering demand. Okay, as they say, necessity is a mother of invention. That's a business necessity that is getting converted into a software, and the engineering processes bring the disciplinary rigor around it to make it more rugged and productize it. Um, so that is how the software engineering is enabling the software development life cycle. Okay, so it is business driven and governed by regulatory imperatives of the respective government agencies from where it is built and who is buying the software, depending on which ecosystem or which land regional laws applicable. Okay, so all that should be taken care of as part of the software engineering life cycle. So the software engineering process, if you say it has multiple stages or milestones, some of which are highlighted here. Okay, there is a requirement gathering phase, then there is a software design. So in the first part of the requirements gathering, you first understand what, as I said, it is a business driven. Software engineering is driven by business needs, right? So first we need to understand what are the business requirements, who are the different stakeholders, what are the business requirements. So it could be a business requirement, could be a functional requirement, or it could be a non-functional requirement in terms of performance, etc. So we first understand what the requirements are. So requirements focus on what to engineer or what to build. Software design talks about the how to build it. Once I now understand what I have to build, what the software product is supposed to do, then the focus is on how I build it actually. So software design and architecture focus on those important questions. Then software construction is actually building the software, so the actual generating the necessary code, building it, compiling it, and all that. And then comes the software testing and verification. Once the software is designed and built or engineered, somebody has to test it and qualify it that it complies uh, with the software best practices guidelines, as also it meets the business requirements provided in the requirements, and it also complies with the software design recommendations provided as part of 2.0 and the step 2 above. So software testing and verification is a very critical piece. It provides you the quality assurance of the software that is built. Okay. So, software quality assurance is the formalization of the software post software testing and verification. So, there is a quality assurance and the metrics management which says that how good the software is, and then the software engineering process and project management life cycles are there. Okay, so this is actually a cycle. We'll talk more about it as we move along. Then there is how we configure and other details, software maintenance, software configuration, software engineering processes, and finally the quality assurance that we provide. So this is a 8-step process. Okay. This eight-step process has various substages, okay, or milestones. So the requirements engineering, where you elicit the gathering of the stakeholder needs, specification, documentation. You provide a business requirement document or software requirement specifications. Okay, then you are also validate the requirements that you have gathered with the respective stakeholders. And then there is a software engineering area where you lay down the architectural boundaries, decide the core technologies with which you have to build the best design patterns, the principles and design patterns to do it. And so the entire decision making around how to build the software construction is where you actually implement it. You do the code generation, unit testing, and code quality assurance. Okay, and then build as part of the software construction life cycle. So you ensure that the build and integration is smooth. Okay, then finally there is software testing and verification, which starts with unit testing, which is actually part of the software construction. And then there are different other kinds of testing like integration testing, system acceptance testing, automation performance testing, load testing, user acceptance testing, etc. Okay, then there is software maintenance. Once a software is tested and goes live, then there is a continuous maintenance around it. So there is adaptive maintenance, corrective maintenance. So then there is a preventive maintenance, particularly when there are when to ensure that the patches are the updated, the security upgrades are all there as a preventive measure. And configuration and change management is supported, so that whenever there is a new enhancement or something, the entire code base has to be managed efficiently. The life cycle of the code base have to be managed efficiently. Okay, then there is process management, where you actually ensure how the entire project management of the different life cycles or milestones of software engineering takes place. So there are different process models like the age-old waterfall model, or the more popular the agile model, etc. So this is where we decide on what is the process model and ensure the governance by implementing those process models. Then software quality assurance is the providing the various metrics to test it on the defects based on the functional as well as the non-functional parameters. And then wherever there is compliance and certifications needed, ensure those compliances and the certifications are they are provided as needed. So this is another way of looking at it, more like a mind map. So different views of software engineering deals with risk management, risk identification, etc. It deals with multiple types of use cases, their metrics, requirements engineering, okay, the user stories, okay, then preparing velocities based on the metrics for those burn down charts that we do as part of the agile scrum practices, and then the testing strategies, right from unit testing to end-to-end testing, integration testing, etc. Then we also do quality metrics in terms of code coverage, and static code analysis, dynamic code analysis, etc. Okay, and then the actual part of the design is what is covered here is different kind of design patterns, including microservices, architecture patterns, anti patterns, etc. Okay, then the kind of CI/CD, continuous integration and development tools and technologies that we'll be using, and containerization. Okay, then how the code can be reused for other purposes and creating shared services model, etc. Okay, some of the best practices in refactoring the code. Okay, code cleansing, peer review process. All these are some best practices. Okay, so and then development methodologies, whether you're going to use scrum meetings or sprint, uh, and the continuous improvement, okay, the or whether it is going to be a waterfall model, etc. Okay, so this provides you a mind map related perspective. Another perspective I wanted to share is a popular perspective, which is called as the periodic table for software engineering. Just as we have periodic table in chemistry of various elements, so there are the different kind of phases and uh, as part of software engineering, which are typically depicted as a periodic table for us to quickly relate to it, and because we are so used to these periodic tables in our school days. Okay, so here, for example, the requirements gathering are all in pink color, and then there is the design related components there. Okay, then the fundamental basics, infrastructure related are in blue. Okay, then the testing related components are there. Okay, this is one of the typical ways today the industry, popular ways of documenting on software engineering processes is a periodic table. There are periodic table for software languages, software technologies, cloud technologies. So periodic table is one of the popular ways of visualizing the different components of anything related to software today. So, and this one depicts on the software engineering concepts. Moving on, this is a very important topic that we're going to talk about. Software engineering, we saw the eight-step process, right? That eight-step process are typically governed under three major buckets. Okay, one is called as the software development life cycle, which is also, I mean, as an acronym, is called as SDLC. So, software development life cycle defines the methodologies for managing the life cycle of the software from its earlier conception during the pre-requirement state to the final go live state and post maintenance stage, right? The entire life cycle. Okay, so it is called a life cycle because it keeps repeating. Software is not right ones and shelf it forever, right? The requirements keep changing, then the demands keep changing, so it needs maintenance, it needs uh, requirement additions, etc., right? Enhancements, different levels of changes are there, right from bug fixes to small enhancement to large feature changes, etc., right? So all this is part of the software development life cycle, and every of these three buckets, right, also has security embedded as part of it in recent years. So recent years means at least as far as I know in the last 10 years. Okay, so which is called as a secured software development life cycle. So we have software development life cycle, and then there is something called a secure software life development life cycle. Similarly, there is another major uh, governance pattern, which is called as the build and integration cycle, which focuses on software process flow, operationalizes the delivery mechanics with the embedded security. So that is the CI/CD. CI means continuous integration. CD means continuous deployment. So how the software that is built is continuously undergoing the process of integration and development, deployment, is what a CI/CD pipeline is about. Okay, CI/CD pipeline is now security is now again integrated into the CI/CD pipeline, and these days it is called as continuous integration, continuous deployment, and continuous security. Okay, so the third major area is on the operational automation. The promotes a culture of culture and collaboration of different teams involved in the software engineering life cycle, right? So there is the core development team, which they include the developers, the tech leads, the architects, etc. Then there is the operations team, who actually focus on the support and operations of that, both are on all different environments, the development environment, the QA environment, the production environment, the staging environment, etc. So these are the two teams which are responsible for the entire life cycle of the softwares. Okay, so DevOps is a set of best practices and governance checkpoints, wherein these two teams collaborate with each other seamlessly. So and again, like in the previous two cases, security is integrated into this governance life cycle. So it is called as DevSecOps. So these three are the core, what we would say, the core triangle for software engineering, where the process starts with SSDLC, where we defines the framework for the lifecycle management. DevSecOps provides the principles of how the teams collaboratively work towards the software development lifecycle, secure software development lifecycle. And CI/CD/CS are the different technology pipeline infrastructures which acts as catalyst and enable the process of continuous integration, development, and security. So going forward, we will be deep diving each of these topics. So first, let us take traditional software development life cycle with the integrated security. Okay, so here we'll be focusing on software development life cycle, secure software development life cycle, and the process details of the same. Okay, so software development cycle life cycle encompasses six major phases. Okay, planning and requirement. Okay, so planning is phase one, where you do the actual requirement analysis, as we talked earlier. We first understand what are the who are the stakeholders in the software that I'm going to build, what are the requirements. Okay, and then prioritize those requirements. Okay, so first I have to understand the requirements, prioritize that, and identify the complexities of those requirements, etc. Okay, once the requirements which talks about what to do is clear, then we move on to the design phase, architecture and design, where we actually build the system design, which will talk about the how the requirements will be actually implemented. So which will enable the implementation into teams. So the requirements analysis and the design, the software design, which talk about what and how are the input to the implementation to we actually build the software in accordance with the requirements and the design specifications. Once implementation is completed, the testing team ensures that the testing is carried out, and it is validated and verified against these two inputs: the requirement analysis, the design, and the regular compliances and other details. So once the testing is also gone through, it is getting deployed in different environments. So there are typically different environments between the development environment to the go live or the production environment. So one is the actual individual developer desktops, wherein each developer, most of the software developments are carried by a team of members. It is not a solo development. So typically it will include multiple developers. Okay, some front-end developers, back-end developers, database developers, API developers, or it could be like a full-stack developers more focusing on different modules within that. Okay, but it will be more than one developer typically, right? So and so every developer works in a development environment, which typically could be his laptop, wherein he has all the source code and the dependencies for the IDEs, etc., either directly in his laptop, or he may have a very thin laptop and connect to a virtual desktop or virtual machine through any of these cloud infrastructures. And so he'll have a very thin laptop access, and the actual control is on the cloud, where separate VM clones are provided for each developer. They can connect to it and do the development. Okay, so that is called as the developer environment. And then there is an integration environment, typically, where each individual's developer modules, uh, which are actually developed and unit tested from their individual clone or individual laptops, is then submitted to a common server, which we call it as an integration server, where all these modules are integrated built into one software piece, which is again tested by the development team itself. Once the testing is successful, it is then moved on to the testing team, which is the QA team, quality assurance team, and they will have their own environments for testing, for depending on what kind of testing they have, whether it is going to be a regression testing, or it is going to be a performance testing, it is going to be a load testing, or it is going to be a user acceptance testing. So depending upon the different kinds of testing the QA team is working on, they might have one or more than one environments for each of these. Okay, for example, the UAT, the end user acceptance testing, which is called as a UAT, is typically hosted in something called as a beta environment or alpha environment or a staging environment, where which stages the production live kind of environment. Okay, and the typical QA environment will have a separate, where they'll do the regression testing. For performance or load testing, they will have a higher end software to or providing the different kinds of scalability in terms of horizontal scaling, vertical scaling, as part of the load or the performance testing. They are going to test as part of the non-functional requirements. Okay, so we talked about the different kinds of deployment. Finally, if everything goes smooth, the software is then deployed into the actual production environment, the production which could be in a multi-cloud environment, or in a single cloud environment, private cloud, public cloud, managed service cloud, or whatever it is, right? So some components can be in a distributed hybrid cloud. So different ways of deployment could be there, or it can be an on-prem deployment. So there are different kinds of deployment for each of these environments. Again, once all the development go live is happening, then there is a maintenance and support on the live platform. When the users start using the applications, and they come up with requirement with the different issues, and the different kinds of support is needed. So there are different severity levels of support, L1, L2, L3, L4, L5, or whatever levels of support, depending on the complexity of the application. So right from L0 to L3, L4 kind of supports are provided, and for that they have various kind of teams, technologies, processes around that. Okay, and then finally, every software also has its own shelf life, right? So softwares also became outdated, and they have to be retired or sunset. So that is also part of this entire life cycle. So this is how the typical software development life cycle uh, continues. Okay, so for each of these phases, there are different artifacts to be documented, so that typically in a large projects, which can run for a couple of months, or and can be maintained across multiple years. So the team who developed, or who provided the requirements, the business analyst, or the developer, or the tester, or the architect, may no longer continue with the organization, or with at least with the team. So the knowledge sharing of what was built, why it was built, and all those things have to be documented. So SSDLC best practices recommend that at each of these milestones, specific artifacts have to be documented and get signed off by the respective stakeholders. Okay, for example, for the requirement analysis, there are two kinds of requirement specification documents, typically called as functional requirement specification or SRS, software requirement specifications. So they are also called as BRD, business requirements document. Okay, so which typically contains use cases or use stories, defines who are the stakeholders, or and the analysis of their. It provides what are who are the stakeholders, what stake they actually have in the system, is what is got documented here. Okay, and the different use cases, their priorities, and the navigation flows, etc. Okay, the wireframes of the screens, all these details are captured as part of the requirements analysis phase. And then it also defines the different measurable outcomes. I mean, how the different cycle milestones as part of this SDLC cycle are actually successful or failure. How do we verify it? So there are some measurable outcomes that are defined at each of these stages. Okay, so for example, requirement completeness and clarity is what we need to measure as part of the requirement analysis, because if the requirements are not complete, or if they are not clear, the entire pipeline will get affected, because I mean, garbage in, garbage out. The fundamental law of computer science is right. If your requirements are not very clear, very precise and complete, then there's a chain reaction, because requirements are the input to the other phases. So the completeness is very important. Similarly, the stakeholders who are actually giving these requirements, they are satisfied with, they approve what is documented, because stakeholders will be at different levels of stakeholders, like the leadership team. Okay, the investors of the organization, uh, the board members of the organization, it could be the stakeholder shareholders of the organization. Okay, it could be the CXOs of the organization, it could be the middle management. So there are kind of different stakeholders. It could be the end customers, and their hierarchy of stakeholders, their end users there, or it could be if it is going to be a B2B business to business platform, or it is going to be a business to consumer platform. Different stakeholders will be there, and different hierarchies of the stakeholders, and each will have a different level of stake in the system. Okay, then providing a traceability matrix is very critical, of how the requirements is the starting point, and how it can be traced through all the other layers of or of the SSDLC life cycle. So what is defined as part of requirements, which talks about what has to be handled as part of the design document. So for every requirement, there should be a specification in the design which talks about how that particular requirement has to be implemented. Okay, that will be typically covered as part of the low level design, where every requirement or every use case is getting provided specific details on how it is getting handled as part of the design strategy. Okay, similarly, what is designed as part of the low level design, high level design, in correspondence with the requirements, should be ensured that it is actually implemented. So every use case, there should be an implementation for that. There should be front end schemes, there should be corresponding APIs, there should be data layer for it, for the persistence. There should be integration touch points for those use cases wherever needed. Okay, the entire 9 yards of the implementation for each of these requirements has to be ensured. So traceability matrix provides that the dashboard view of how each requirement can be traced across the entire life cycle of software development. Okay, so and the main stakeholders of the requirement analysis is the actual business team who actually drive these requirements. Then we're talking about the system design. As we already talked, there are different kinds of documentation. A high-level documentation provides you the high-level architectural blueprint, the technology choices, the tools and technologies, alternative technologies considered, and what is the rationale for selecting the current technology stack or the design patterns, etc. Okay, then there is a low level design where for each of these requirements we deep dive into how the implementation should happen, which will encompass various kind of documentation and visualizations, including entity relationship diagrams, data flow diagrams, architectural diagrams, integration diagrams, etc. Okay, again measurable outcomes in terms of the design coverage for the requirements. Okay, then there for UI UX prototypes, how the design coverage is there, etc. And the main stakeholder here is the development and architecture team, and typically it is the architecture team who holds the ownership for it. Okay, the implementation is the next phase where the actual source code is built. Okay, then the source code repositories are managed, and the configuration and the build scripts around that are also maintained and managed. Okay, so here the metrics is the code quality metrics. There are various ways of understanding the code, like the unit test coverage, etc. are some of the important measurable outcomes. Okay, and the bug rate density, etc. Okay, so development team or the actual engineering team is the main stakeholder here. Testing team, again, they actually verify the code tested. They are responsible for preparing various artifacts, including the test plan, how they're planning to test, what kinds of tests they're going to do, whether regression test is needed here, whether system test is needed here. Okay, whether performance test. So they'll identify different kinds of tests and plan for those tests. And for each of these kind of tests, there will be test cases, and then after testing the actual bug or the defect reports, the test summary reports. Okay, and they'll try to automate. Today with a lot of automation processes are there for testing, so they will enable all these automation tool sets available wherever possible. Okay, and they have their own metrics for measuring the outcomes. So they have the test coverage, defect detection rate, etc. Okay, so while the development team is to ensure that the requirements are all met and it is bug free, the testing team will also ensure it by challenging the development team with identifying more bugs. Okay, the more they discover it, the testing team is supposed to be more efficient, because they have identified more bugs. Okay, then there is a deployment team where deployment phase, where they actually deploy it to the different environments we talked about, right from the development environment, integration environment, QA environment. Okay, then the staging environment, production environment, etc. For each of these, there are different artifacts like release notes, setup instruction, installation guides, deployment scripts, configuration files, etc. Okay, then there is their own measurable outcomes like the downtime metrics, rollback frequencies, etc. Operations team is mainly in charge of this. Then maintenance team is the actual development and support team, the who actually handle the maintenance. So they are responsible for maintaining the change logs, patch updates, performance of the performance reports. Okay, incident responses, etc. Okay, so the metrics here include a mean time to recover, customer satisfaction scores. Okay, this is the long run scoring of that application, the long run maintenance and support ratings. Okay, so this is again visualization of the different artifacts. Requirement analysis focuses on artifacts like SRS and use cases, which is input to the system design. Okay, the outcome is the approved requirements, and then the system designs artifacts are high level design, low level design, ERD, etc. Then which is an input to the implementation team. The outcome here is the validated design. Okay, then the artifacts for the implementation is the actual code base and the repositories of the different environments. Okay, which is an input to the testing team. Outcome is the working code base. Okay, the testing team again prepare these artifacts, test case, test plans, defect logs, etc. Okay, and the outcome is the tested and verified product. And the deployment team takes all these requirements, I mean all these inputs, and then deploys it into the various environments. Okay, their outcome is the software in production. Okay, artifacts is release notes, installation scripts, etc. Maintenance day provide the artifacts related to patches, performance logs. Outcome is stability of the product. Optional is the retirement. So certain at the end of the life cycle of the product, if it has to retire, so the artifacts are the migration of the what will happen to the users who are already using it, what will happen to the business functionality. Okay, whether you have to re-engineering it, re-host it, or rebuild it, or so the different ways by which old application can retire, a new application can be brought. So we different analysis of that. Okay, so then the successful decommissioning of that. Okay, so so long we were discussing about the different milestones as part of the software development life cycle. Now we are talking about secure software development life cycle. How securing the software becomes a very important process here. Okay, so the phases of secure software life cycle is what we are talking about here. So requirement, design, deployment, testing, and deployment is a typical cycle. So here in each of this we identify what are the typical security threats. Like for requirement, we have threat modeling and design review. Okay, well, we do provide static analysis for security threats, security testing, and code review during the development time. So something are during design time, during requirement time, during design time, during run time, and during actual production time. Okay, so as part of the analysis phase, we identify the security requirements and potential risk early. Okay, and design security data handling, user access control, and threat mitigation as part of design. Development implement secure coding practices and scan for vulnerability. During testing time, perform security testing, vulnerability assessments, and penetration testing. During deployment time, ensure secure deployment practices and monitor for vulnerabilities. Maintenance is a continuous process of applying security patches. Okay. So the behind SSDLC is that testing is now left shifting. Okay, so that we start. I mean, as they say, the prevention is better than cure. So the focus is to not to find last minute surprises or other shocks. Okay, to left shift it as per right from the requirement phase itself. You are cautious about what could be the potential security threats to the software and how could I mitigate those risks. Okay, so that shifting of to the left or left shifting is one of the most important I mean uh, uh, inputs as part of the SSDLC life cycle, and so that the overall success of building a software is higher. Okay, so while traditional focus on SDLC is more reactive, the secure software selection is proactive, right? Because we are we are left shifting, right? So because of that, we are preventing it ahead of time. So even before the risk could arise, we start thinking through it, planning for it, and mitigating it wherever possible or how much are possible before the actual security risk occurs. Okay, so this is again some metrics from the industry on how 70% of the major digital transformations processes fail because of delayed security challenges or threats. And SDLC, when most of the issues are captured as part of the maintenance, which adds to the overall total cost of ownership, which adds to the cost. Defects fixing the later stage, right, adds more to it. So the earlier we fix it, it is better. Okay, So 9 to 10 projects face major overruns. Okay, 1 in 6 ICT projects have an average overrun of 200%. Okay, so these are all some metrics from the industry. Okay, so the earlier the stitching time saves 9. Okay, the earlier we start detecting all these security threats, we can we can reduce the overall cost and overall customer satisfaction also. Okay, I mean, instead of the customer coming and complaining and then we fixing it, we fix it proactively so that the customer satisfaction is much higher. Okay, so with this, we talk about the briefly talk about the different phases of SSDLC. Okay, so I mean, we'll be deep diving them as separate sessions as part of the overall uh, agenda. But now we will only touch upon briefly on each of these phases. So for the requirement phase, the stakeholders are typically the product owners, the CISO, the business analyst, the risk officer, etc. And each of them have their own key responsibilities. So the product owner defines the business requirements. He is responsible for the overall requirements of the product. So he will talk to different stakeholders, including the customers, the partners, partner networks, the customer networks, the board members. Okay, the leadership teams. Okay, then comparative product, a product comparison of competitive products available in the industry, etc. And he'll come up with the actual product requirements. Okay, CISO, Chief Information Security Officer, will be overall in charge um, for the security and the information related to to the life cycle of the software. Business analyst will actually analyze the business requirements by talking to different business stakeholders, including the product owner, the CISO, the end customers, okay, the competitors, etc., and document the actual requirements which will be used by the technical team, the design team. Okay, then the risk officer will ensure, he'll be part of the CISO, and he will ensure that any compliances related to government and other regulatory uh, uh, needs are met as part of the overall requirements. Okay, I think just a repeat of that. Okay, then coming to design phase, typically it is the security architect, the solution engineer, the data architect, the enterprise architect, the solutions architect. That the different architects work on different scope of architecting, and they are all responsible. I mean, not all the architects are given here, but there are multiple kinds of architectural roles, and each have their own key responsibilities. Okay, for example, if you take a solution architect, he is responsible for the entire solution for that particular solution that you are building, which could be a product or a platform or a SaaS solution or whatever it is, right? And there is an enterprise architect who is responsible at an enterprise level how these platform or these product, I mean, stitches into the overall ecosystem or the IT landscape of that particular enterprise, is the enterprise architect's role. The technical architect is responsible for the technology choices, the identifying the tools and technologies, the design patterns, the HLD, etc. Okay, while solution architect provides a larger technical roadmap. Uh, okay, and the reference architectures, etc., software governance, architectural governance of ensuring the what is built is in alliance with the best practices defined as part of the architectural guidelines. Okay, the data architect, including the schema design, identifying what kind of database you have to use, whether you have to use a relational database or NoSQL. If it is a NoSQL, whether it is going to be a graph model or a key value pair model or a JSON based document model, etc. Okay, and you will also understand whether you have to go for a polyglot model, or how the persistence should happen, how the life cycle of the data has to be managed. Okay, so what level of transactional the asset principles need, etc., have to be identified. Then the UX's team and its lead are responsible for actually creating the user interfaces for all the requirements, all the use cases. Okay, the kind of controls, the kind of navigation flow, etc., the look and feel of those in line with their actual end users requirements. Okay, so then there is the implementation phase, which is actually the core engineering team who will write and review the code, the DevOps engineer who will support as part of maintaining the CI/CD pipeline, the security champion will ensure that the SSDLC is implemented. That means security, the left shifting of security is happening right from the requirements phase. Okay, the testing team includes various stakeholders, including the penetration testing, the actual QA lead, the test manager or project manager, the auditor providing the quality assurance, etc. So they'll provide different kinds of testing and test plan, test governance, etc. The key security division is for release approval, vulnerability of the various kinds of risks the product could potentially be exposed to. Deployment, the operations manager, the identity access management specialist, the network engineers, the release managers, the cloud architects, the cloud engineers, etc. All of them will be responsible for the deployment phase. Maintenance and support is the support team, the SOC analyst will be there, the executive sponsor will be there who will support the life cycle of that application, who will ensure the return on investment, because once you build it, unless you keep returns, you start getting revenues out of that product, or at least there is some need for continuing maintenance of that, is actually needs an executive sponsor. If it is going to be if it's going to be a revenue making product, or it is going to be a back office support product, depending on that, the sponsors of those product lines will change. Okay, this is again the different artifacts that as part of the SSDLC life cycle. Okay, so phase one. So for each of these phase, what are the tools typically available? Okay, for example, as part of the requirements phase, okay, which includes security activities like threat modeling, requirements documentation, compliance review, then deliverables of security requirements, risk assessment. So the focus is on how the SSDLC in part security is captured here. Okay, starting with the traceability for those requirements, and what are the different kinds of tools available for as part of the requirements phase for security. Microsoft threat modeling tool is there. Then there is OWASP tools. Then there are tools like SAST, IAST, etc. We will be covering them as part of the subsequent slides. Okay, then there are different security gates the requirements phase has to pass through: approved threat model, signed off security requirements, etc. Okay, so after that comes the secure design. From secure requirements to secure design, security activities include a security architecture review as part of the architectural phase. Here, security design patterns where the privacy by design is considered. Okay, then deliverables include security architecture document, attack surface analysis, etc. Measurable outcomes includes typically zero point 0.5, less than 0.5% of security defects or kilo lines of code. Per kilo lines of code is what could be a metric here. I mean, there could be other metrics. This is just an example. So, crypto standards compliance 100%, etc. Security gates here are include security sign off on design, mitigation plan for identified risks. Then comes phase 3, where secure implementation is happening. The security activities include secure coding standards as part of the code, SAST scanning, secrets management, etc. For the different kinds of encapsulation needs, including passwords and other critical data, which has to be maintained within a locker or vault as part of the development phase. Okay, then there is the SAST reports. Based on the SAST testing, the various kind of reports of that, code review logs for security threads, and documentation of the different kinds of security implementations that have been done. Measurable outputs is in terms of less than 90% of issues are remediated, etc. Security gates include critical vulnerabilities has to be less than 10, secure coding training completed, etc. Okay, then comes secured security testing. Here, DAST and IAST are the different technologies available for testing. Penetration testing can be there. Security automation will be there. And then pen test report is there. Vulnerability management. These are all the things currently industries are practicing to ensure secure testing. Okay, measurable outcome include OWASP top 10. Uh, okay, with the top 10 coverage for 95% or greater. Okay, so similarly 72 hours of vulnerability remediation is what highlighted here. Then security gates, critical vulnerabilities and pen test sign off. Okay, secure deployment. So here include infrastructure hardening, ensuring that the infrastructure that we are used does not have any OS relative patches or security holes, etc. Security baseline configurations. Okay, virus patches, etc. Antivirus patches, etc. Okay, deliverables, hardened environment, incident response plan. Okay, then CIS compliances. Okay, security gates are infrastructure security sign off, IR plan. Okay, phase 6 is security operations, which includes the RASP protection, continuous monitoring, threat intelligence, etc. Okay, the deliverables are SOC reports, vulnerability feeds, etc. And MTTR is one of the measurable outcomes here. We'll be looking in greater depth of these concepts here. Okay, so the tools for input are WAF is there, RASP solutions are there, then SIEM solutions are there, the threat intelligence platforms are there. Security gates are the false positives and automation and auto remediation rates. Okay, so these are the typical part of the SSDLC secured software lifecycle processes. So with this, we complete the traditional SSDLC concepts overview. Now we move on to the next related concept. As we saw that there are three major pillars of secure software engineering. One is SSDLC, which we saw. The second is the DevSecOps. So we will take a brief overview of how traditionally these DevSecOps is being handled. So we'll start with DevOps, then move to DevSecOps, and the process details of the same. So DevOps was conceived to dismantle the organization and procedural silos that traditional operated software development. So typically, the development team and operation teams were there are not a very synthetic or very synergetic workflows between them. It was more either manually, person to person kind of dependencies were very high. So that was where the need for a seamless process flow and governance between these two teams to make business as usual very successful. Okay, so that is the idea between continuous integration and delivery or deployment. The CD stands for delivery, it also stands for deployment. Okay, sometimes it is called a CDD, which is called as continuous delivery and deployment. Okay, So this is a very very standard. You will see that all over the internet is that how the CI/CD pipeline typically contains all these components, right? So right in from build planning to building to testing to deployment to operate to observe to continuous feedback to discover. So this is a endless loop. Okay, if you see some of these phases are actually part of the SSDLC. So we so now you should start stitching SSDLC or overlaying SSDLC on the DevOps. Okay, because both are trying to solve the same problem. Okay, so this is a loop. The SDLC cycle is very typically captured here as part of a loop representing infinity symbol or a horizontal 8 or however you want to look at it, having different phases where it becomes a continuous process. Okay, on the one side is the development team and the other side is the operations team. Both these teams have to seamlessly handshake between them because both are dependent on each other. Okay, so this is the funda between the DevOps. Okay. So DevSecOps is an extension to DevOps where security is integrated as part of this life cycle. Okay, so right from the stages of the planning, building, testing, deployment, operate, and monitor, all the six phases, which also typically follows the SSDLC life cycle. Okay, security is brought built into two major area, which is pre-production, which is managed typically by the development team, and the production, which is managed typically by the operations team. Okay, and this is where the security is part of the every layer here. So, for example, as part of the build, as a planning, the threat modeling, which we already saw as part of the SSDLC cycle, is also highlighted here. Threat modeling, change impact analysis, as part of the build or the pre-production, pre-commit hooks of software, SAST, DAST, code review, all these things are part of the build. As part of the test, we have the DAST. Okay. Then, as part of the deployment, access and configuration management, chaos engineering, pen testing, etc. So all these things we already discussed as part of the SSDLC cycle. So operate is between the log collection, patching, etc. Okay, WAF, RASP, etc. Okay, then there is monitoring, which includes SIEM, vulnerability monitoring, access control, etc. So all these processes, best practices, technologies, tools, all will be part of the CI/CD pipeline for rightfully implementing the SSDLC lifecycle. Okay. So DevSecOps is the evolution of DevOps that bakes security into every phase of the secure software development lifecycle. Okay. So there's a continuity from SSDLC to DevOps. Though these are two appears to be two different concepts, they are all trying to solve the same problem. Okay. They are interrelated to each other. Okay, DevSecOps, the shift left security, which we already discussed. So it introduces security checks at the earliest stage of the development. So stitching time saves 9. Automation, use tools to automate using code analysis, vulnerability scanning, etc. Collaboration, okay, foster shared responsibility among developers, security experts. All the stakeholders have to collaborate with it. Then continuous monitoring for tracking the threats and vulnerabilities. Compliance as code. So automate regulatory checks using scripts and policies. Okay. So DevOps was only focusing on speed and quality of delivery. Here, speed, quality, and security also comes in as part of the focus. Security integration was post-development in DevOps. In DevSecOps, it is embedded throughout the SDLC or other SSDLC. Okay, team composition is development plus operations in traditional DevOps. When it comes to DevSecOps, the security teams also are also involved here. Okay, then testing is functional and performance testing is DevOps. Here there are security specific testing also integrated as part of the DevSecOps. Tools for CI/CD, version control, etc. CI/CD plus security scanners, compliance tools, etc. Are what the typical tool sets for DevSecOps are. Okay. So here some more, understanding between traditional security and DevSecOps. In terms of timing of security at the end of the software development cycle, which is right, which is the right end of the pipeline. Here, DevSecOps is left shifting, so continuous and integrated throughout every stage of the SDLC for planning, from planning to monitoring the entire SSDLC lifecycle. There are right checkpoints or security gateways to ensure that security lapses are covered. Then core process, linear waterfall processes where security is a distant separate phase. So in typical SDLC model of waterfall, security was handled at a much later stage. Here in typically in the agile model, security is inbuilt as part of the entire management process. Okay, so then responsibility, the sole responsibility is siloed, specialized security team was involved. Here it is not so. Security team is part and parcel of the entire SDLC life cycle. In fact, they'll have a participative role as part of the Scrum or the regular meetings and brainstormings. Okay, primary focus is on securing the network perimeter and infrastructure as part of the security team. Is here the holistic security of the application, so they are involved directly in the application level security. Okay, tooling often involves, as far as traditional is manual security reviews and separate disconnected scanning, but here it is all part of the automated CI/CD pipelines when it's come to DevSecOps. Okay, pace and velocity create significant bottlenecks, delayed release cycles because of late realization of the security threats. But here it is more proactive when it comes to DevSecOps. Outcomes is reactive in case of traditional security. Here it is more proactive. Okay, culture, it is of more often antagonistic, with security viewed as a department of no that blocks progress. This is more of a historic context. When people talked about DevSecOps, there are a lot of resistance of why we talk about security now, why you spend so much on security and all that. But now I don't think that culture still exists, because everybody now realizes the importance of left shifting the security as part of the SSDLC process. So DevSecOps activities typically involve multiple stages, which are here categorized as 7 to 8 steps. But of course, these steps can be either further increased in the number of steps, or aggregated into a short step, depending upon from organization to organization or from project to project complexity and their priorities, etc. Okay, so stage one is more of the planning phase, where activity teams define the security requirements, uh, the same rigor as functional requirements. Okay, so the security was just one small part of non-functional requirements in the traditional way, but now it is becoming a separate line item, or a separate document, or separate phase of the planning. Okay, so then, as part of the stage two, during the actual development, the activities include developers are trained in and adhere to the secure coding standards. Okay, actively working towards the prevention of the security threats like SQL injection. Okay, so the cross scripting threats, etc. Okay, so these are very, very, very. Infamous threats, or very powerful, or very frequently infecting threats, security threats for today's software. So the earlier we handle it, it is better. Stage three is build and deploy, where the continuous integration pipelines orchestrates a series of automated security tests. Then comes stage four, where we do the actual testing. The pipeline executes the tests that simulate real world attacks to uncover various security vulnerabilities that are only discoverable at runtime. So during the runtime, there could be a lot of security threats which cannot be identified as part of the design or coding time. So those are things where the runtime testing have to be identified. Then finally, in stage five, when you go live, when you release it, so the security, the packaged application, which is typically on a container like a Docker, is scanned for the known vulnerabilities. Okay, then the stage 6 is the deploy in the configuration. So after, as part of the packaging and the release release management is stage 5. Stage 6 is the actual deployment, where you do the configuration validation. After deployment, automated checks to confirm that the live production environment's configuration has not drifted from the source intended state defined in the documentation as part of the testing. Okay. Uh, so IAC means infrastructure as code here. So today, infrastructure configuration of scaling in and scaling out of infrastructure deployment or assignments are today managed through codes, and through the agentic AI. These codes are also generated by the system. Okay. So stage 7 and 8 is the post go live maintenance and support activities relating to security. So with the brief overview of DevSecOps, which actually followed the SSDLC, uh, we now move on to CAE/CD and CS, that is continuous integration, deployment, and security. Uh, the traditional way of seeing. So we will see what is CACD, CACS, and CD. Okay, and the process details around that. Okay, so similar to how we I mean represented DevSecOps as an infinite symbol, or a horizontal 8. So typically the CI/CD pipelines are also shown that way, where we start with the planning, the coding phase, the build phase. Okay, so the testing phase. Okay, so this is how the flows from planning to coding to building. Okay, building means the release management, compiling, generation, packaging, etc. Okay, so to testing, to release management, to deployment, to operation. Okay, to monitor. Okay, this is how the flow is. Okay, this 8. Okay. Continuous integration automates the process of the integration code changes from multiple contributors. As I said, at the individual developers within a team, there could be multi-teamed development cutting across cities, or across uh, departments, or even across geographies. Okay, or even across companies. Right, there could be software development, particularly large. Projects which can multiple teams will be involved. For example, a company, a banking, somebody is building some for banking software. Some part of the software can be built by a company like TCS. Some could be built by Cognizant. Some could be built by some third-party vendor. Some could be on a in-house development. Okay, so multiple teams can participate in building the software. Some could be developing from US, some could be from India, some could be from China. So there could be a geographical segregation between teams. There could be a corporate segregation between teams. Okay, there could be a stack level segregation, front end teams, back end teams, etc. Okay, so continuous integration needs to integrate, cutting across all these I mean different layers or different sources of the source code. Okay, and building it, automating the building process, code committing process, building the process, then automated testing and the feedback loop. So this is the typical cycle of the continuous integration. It is going to be continuous because the product life cycle is to be continuous or iterative. So first we have release 1, release 2, release 3, version 1, version 2. So there are different release managements, version management, etc. So each of this the code base has to be touched. Sometimes the code base have to be branched for different versions, etc. All these things are part of the continuous integration life cycle, where they catch bugs early, ensure code base stability, reduce integration conflicts, etc. Continuous delivery or deployment is another major part of the CI/CD pipeline. Okay, here continue CD automates the deployment of validated code to production environments. Every change that continuous integration is automatically released to the users. So artifacts, the code artifacts are there, the documents repositories are there, Docker image repositories are there, image repositories are there, video repositories. So all these artifact repositories have to be um, uh, the corresponding artifacts have to be deployed to the respective uh, version control systems or to the file repositories, image repositories, etc. Okay, then environment deployment to the different environment we talked about, right from the integration environment to the staging, QA environment, staging environment, production environment, etc. Okay, and then there is the automated testing, so end-to-end testing for the different environment, particularly on a UAT environment or a staging environment. Okay, performance and load testing automation, etc. Roll back the mechanism whenever there is a issue or a bug or even post go live, because of some reason they have to revert back or roll back, and the previous version has to be automatically deployed. So all this is part of the continuous deployment and delivery life cycle. Many times it happens, right? The release management will release it, but for some reasons, some constraints or reasons, they have to revert back to the older version, because there could be some bugs which escaped through all the SDLC cycle, and which go live, they discovered it, and they have to revert back until they fix it to the older version, etc. So the continuous deployment delivery handles all those tasks. So deliver features faster, minimize deployment risk, ensure zero downtime releases. Okay, these are some of the key goals of the continuous deployment and delivery framework. Okay, then continuous security, integrate the security checks throughout the CI/CD pipeline to identify vulnerability, shift left security. This we already talked about. There are different ways to do that, which include the static application security testing, which is called as SAST, which scans the source code for vulnerability. This is static, or the runtime or development time or design, build time kind of uh, role this SAST plays. Then there is a dynamic application security testing, which is called DAST. During the testing time, test running the applications, threats, example, OWASP, ZAP, etc. Then dependency scanning checks for the third-party libraries. Particularly, there could be, as any software will include a lot of third-party libraries, which could be open source or commercial or whatever combination, free open source, commercial open source, COTS products, etc. Right, all those dependencies, they should ensure that they are available in all the environments we talked about. Okay, the QA, the staging, the production, etc. The security detection, so prevent accidental exposure of the credentials, like the user ID password of different environments, like in the QA environment or the production environment, is very, very important, because yeah, I mean, people should not go and mess around. Even the technical team or the support team, some developer or some operation engineer should not have access to the production environment configuration passwords, etc., so that he can mess around with that, right? We should ensure that they are all put in the respective vault or secured layers, multiple levels of security is there. Whoever is um, as a is authentic user and is authorized to access it should only access those details. So all this is part of the continuous security processes. So typical CI/CD process looks like the flow chart here. I mean, this is just a reference level, but things, the reality will be much more complex. Okay, so the continuous integration, we have the code commit from build to unit testing to SAST based continuous security, code scanning, security detection is there, then dependency scanning on third party libraries. Then the process goes on to artifact repositories. Okay, corresponding, once all the security checks are there, it goes to different artifact repositories, like for the source code version management systems, or for the Docker images, or wherever it is, whatever kind of artifacts repository are there, it goes there. Deploy to staging, right? During that, you do the DAST scanning, and end-to-end testing or performance testing. Okay, if it is for manual approval, wait for the workflows of manual approval release, it goes to auto deploy or the production. If it is not manual, it is automated, it automatically goes to the auto deploy production, then production deployment, then you do final round of smoke testing. Okay, then actually the monitoring and rollback as part of the business as usual continuous monitoring, then continuous feedback which goes back to the coding team to add back to the build cycle. This is the typical cycle for CI/CD/CS, which incorporates the entire SDLC or SSDLC process, um, and the DevOps SecOps pipeline. Okay. So CI faces the code commit. The developer pushes the code to the Git or other repositories. The build, the code is then build or recompiled. Then automated testing is that there are different ways of compiling. Just-in-time compilers are there. So depending upon the nature of the technology, the tools, the code language, and the need for compilation, different kinds of compilation can be there. And then the CS phase run SAST for SQL injection example here. Then the dependencies can checks ensure that some of the libraries, jar files, or DLLs or whatever it is not missing. Security detections are identify the block commits, etc. Okay. And then artifact storage as part of the CD is a secure upload to a repository, Docker Hub or Nexus, etc. Okay, then staging deployment time you do the DAST and end-to-end performance testing. Then there's a feedback loop, failure trigger alerts, metrics from production feed, etc. Going back to the CI phase for continuous code commits, etc. Okay, so this again another way of representing the loop. Okay. So with that overview of SSDLC, with the overview of DevSecOps, and with the overview of CI/CD/CS pipelines, we move on to another major related topic, which is called, which we can call it as a traditional process tools and technologies for the integrated pipelines. We saw three different pillars. How these three pillars, what kind of technology tools will supports the efficient management of these three pillars is what we are going to see as part of this phase. I mean, this section. So we will be here talking about the key practices and tools, automated security testing, key insights per phase, runtime protection requirements, continuous compliances, threat monitoring and response, roadmap maturity, etc. Okay. So the key practices and tools for secure coding and design includes threat modeling, identify, which includes 1 minute. I have somebody there. Sorry guys, there was somebody at the door. Okay. So the key practices and tools is what we are focusing on. Okay, so for secure coding and design, the different tools and technology available is one is for threat modeling. Okay, identify the risk during the design. For that, very popular tools for it is the Open Worldwide Application Security Project provided Threat Dragon. Okay, so the OWASP or the Application Security Verification Standard project provides. So OWASP is the project which provides a standard which is called as ASVS or Application Security or Verification Standard. So provides a basis for testing web application and technical security controls, and also provides the developers with a list of requirements for secure development. So this is a very standard organization providing some of the best practices for application security and verification. Okay, so there are different tools available for it. For example, Sonar Lint, then Sync IDE are available for as part of the plugins. You can plug into some with the most of the popular IDE developer integrated developer environments. Okay, these plugins. Okay, some of them are open source, some of them we have to procure. Okay, open source have limited capacities, and I mean licensed ones provide you more comprehensive things. Okay, OWASP identifies the top 10 as far as of the 2021 is the uh, typical threads like the broken access control. Okay, falls to. Okay, so I'll probably have to blow it up a little. So broken access control talks about fail to keep out users out of the restricted areas. Okay, so the access control is broken. That is what broken access control is. Then cryptographic failures, weak encryption leaves sensitive data exposed. Then there is SQL injection, where lets attackers inject a harmful code like SQL. Okay, so this is a very very risky threat. Typically, if you are not on guard. Okay, then insecure design flaws itself, but at a design side it creates a lot of security vulnerability. Security misconfiguration, incorrect settings opening the door for attacks. So when you're configuring the ACL access control levels, there are misconfigurations, that has a huge risk. Okay, then vulnerability of outdated components, particularly outdated libraries or outdated patch files, virus, antivirus software, etc., could create a potential threat. Identification and authentication failures, then software and data integrity failures, security logging and monitoring failures. Okay, and server side request forgery. These are what has been identified by OWASP as the top 10 list of web related security threats. Okay, so here you use a metric, provide application developers and application owners with the yardstick, which, so you have to provide a metric of how you want to measure the security threats. Okay, use guidance. Okay, and use during procurement, provide a basis for specifying the application security verification requirements in contrast. Okay, so this is actually the site of OWASP. So which provides you a lot more details on what OWASP is. It is latest version, etc. You can take a look at it. Okay, this is very useful piece of information. Then automated test security testing, we have at the different stages different tools and techniques available, and each of them have a different purpose to play. For example, at a coding level, there is something called as SAST or static application security testing. The sample tools include, example tools include Sonar Cube, Checkmark. Sonar Cube is very popular. Okay, and the purpose it's scan the code for vulnerabilities during the coding time. So it is a static code, right? It is not during the runtime. You give the source code to it, it traverses through the source code, scans through it, and then identifies different security threats. Okay, then there is a build level software composition and analysis tools, which is called a SCA. Okay, tools include sync and dependency tests, which is during the build time. Okay, while packaging, compiling, etc. SCA is an automated process that identifies and manages open source software components within a code base. Open source, I think, left, right, and center today, most of the software development uses some kind of open source technologies. Okay, and open source always, I mean, have the potential for risks, because they come from a larger from a open consortium or support, so larger developers are managing it, so the chances of security threats are higher there. And depending on the kind of open source also is very important, whether the open, so there are open source licenses which are specific for academic purposes, I mean, yeah, copylefts, copyrights, all these things are there. So as part of the SCA analysis, we should also identify what are the open source libraries, their dependency software that are being used, whether these software components are legally um, supposed to be used in a production environment. If they are legally supposed to be used, whether these softwares have security threats within themselves. So I can write a code which is secure through by taking care of all the SSDLC life cycle best practices, etc. Right? But when I depend on third-party softwares, particularly open source softwares, which are mostly free or available in the open market, I cannot guarantee that it. I mean, it is also compliant with all the best practices of secure software development. So SCA helps in identifying most of them there. Okay, then during the test phase there is dynamic application security testing, which is called as DAST. Okay, the tools include ZAP for our OWASP, and there's something called as burp suit, etc. So the purpose here is to testing method that analyzes a running application. So during the test time, the QA team do the various kinds of testing. There they also do for security testing, like regression testing, like performance testing, load testing. Security testing is where they use the tools like ZAP as part of the DAST. Then there is infrastructure as code, IAC scan related thing. The tools like TerraScan, CheckOV, etc. provide for as part of the cloud provisioning and during the infrastructure deployment time, etc. So automated security testing includes SAST, DAST, and IAST. Okay, SAST is static application testing, DAST is dynamic application security testing, and IAST is interactive application security testing, which tries to provide a bridge between both. SAST is for white box testing, DAST is for black box testing, while IAST provides a combination of both. Okay, tools are developed to address the flaws in SAST and DAST. So they are dynamic and identify issues during operations like DAST, but run from inside the application server and evaluate like SAST. So SAST is code level, right? From the IDE you integrate and you build it. So that feature is provided by IAST also, but at the same time it also provides runtime security checks. Okay, like DAST. So it tries to build the best of both kinds of tools in IAST. Okay, so this is another closer look of the various security techniques or tools. Okay, so there are so SAST scans the source code for vulnerability. SCA identifies the vulnerability dependencies, libraries, and frameworks, particularly on the dependency libraries is where the focus is. DAS is for runtime application testing. IAC is for the deployment infrastructure at the cloud level, public cloud, private cloud, and the misconfigurations there. Okay, when for early part of the SDLC is where SAST is as part of the coding time itself. Okay, SCA is during the build process. Okay, after coding, when you actually do the CIC integration, you integrate from different sources and do the build. The SCA based testing is there. This is particularly important because in a multi-team development, the dependency softwares that each one use sometimes could overlap and could and when you integrate them, they may fail. Individually they may work, but they because of the dependencies on the versions. Okay, I may use open source version for logging or something. Okay, I can use version say 1.0 or 1.2. Okay, the team at the other end may use the same logging software, but they may use for some the either a older version or a newer version 2.0. When I integrate these two as part of the integration testing, uh, that time there could be a discrepancies in terms of the version management. So two old version, new version may not work together. So these are some kind of examples there. So that is those are the things we need to know as part of the build cycles. Okay, then during the DAST, during the testing team will do the late SDLC testing, and during the continuous integration and development is where the infrastructure code security scanning can happen. Okay, so what it analyzes, SAST is on the source code and the binaries and the byte codes. Okay, SCA on the dependent libraries, open sources, etc. Okay, DAST is more on the actual request response flows at a API level or HTTP level, web interface level, etc. So it's basically runtime behavior. IAC is based on the Terraform or the configuration for deployment, the testing the YAML code bases, cloud formation, Docker files, configuration files, etc. Okay, then the detection scope is SAS focuses on logic flaws, syntax related issues, hard codings, okay, injection risks, etc. So code quality issues, code coverage covers all these issues. Okay, SCA covers more of the dependencies on the licenses, compliance, etc., which we talked about. Okay, DAST is focusing on the runtime vulnerabilities, configuration errors, authentication flaws, etc. And IAC security more on identity access privileges, exposed storage, non-compliance of sources, etc. So strengths is find the flaws at left shift, right? Full code of visibility is there. SCA is critical for supply chain security. Okay, DAST is more for real world simulation, particularly during performance and load testing. Okay, and IAC is during the toxic cloud environment, particularly when deploying on a public environment. You ensure that there are no security holes. Okay, so limitations again in each of these is that SAST, because it is leftmost at a compile time, there is high false positives there. Okay, misses runtime. So some what looks very green at a SAS level may not look so green at a SCA level or a DAST level. Okay, so when it comes to SCA, cannot detect the custom code flaws. So it cannot detect at a what SAST is supposed to do. Okay, limited to no vulnerabilities, to known vulnerabilities in the databases. Okay, then DAST comes requires running the application, so it requires a runtime environment, whether it is in a load test environment or a performance test environment. So that kind of in simulation of those issues have to be identified. So it will be slow because it is based on the actual runtime iterations. No, it is very difficult to capture it because only if you are able to simulate the right kind of security threat as part of the testing, we can simulate it. But trying to simulate it becomes a challenge. Many times what will happen is that it will work perfectly well in the staging environment, QA environment, but it will fail in the production environment because we are not able to simulate the actual issue in these environment, the other environments other than production. Okay, so when it comes to limitations for IAC, it is more limited to infrastructure layer. Okay, it doesn't focus on the other layers. Key tools we already saw. So best for also we have already saw. So output here is SQL injection is there here, in terms of SCA, in terms of the library dependencies, etc. So like that for every layer we do it. So code commit SAST and SCA, build is IAC, deploy and staging it is DAST. Okay, and this is again a typical SSDLC life cycle where requirements, as part of requirements to design, you do threat modeling. Between design and implementation, you do the secure architecture. Between implementation and testing, you do the SAST and SCA. Between testing and deployment, you do the DAST and pen testing. Between deployment and operations, you do the IAC. Between operations and monitoring, you do the RASP or the SIEM, and then the feedback is a continuous process. Okay, so automated security testing includes requirement design, implementation testing, deployment, operations and monitoring. All the phases of SDLC have to be have some security checkpoints or gateways. So there are different techniques at each of these gateways to be performed. So threat modeling, we saw that OAuth and ASVS is there. Security requirements, OWASP top 10 proactives are there. And then compliance mapping for regulatory standards like GDPR, European standards, or the payment card industries data security standard, PCI DSS kind of compliance related testing. All this has to be done at the requirements gathering itself. So OAS threat modeling, Microsoft threat modeling tools, ERIS risk, etc. are some of the key tools available. When it comes to the design, secured architecture review, attack surface analysis, privacy by design. So these are some of the important security techniques. Okay, and here the tool sets includes OWASP application security verification standard, ASVS, OWASP cheat sheets, and secure deployment elements, SD elements. Okay, and security detection elements, sorry, secret detection elements. Then testing, there are DAST, IAST, we talked about penetration testing. Okay, so you penetrate into the entire layers and tiers for as part of penetration testing of for the security threats. API related security testing is there. API gateway level you do it. Okay, at a service mesh level we can do it. Deployment as infrastructure as a service, so you do the scanning of the various Terraform and other configuration, YAML and other configuration files. Then container level security as part for the Docker configuration hardening, secrets management, etc. Operations are runtime protections, WAF, or web application firewalls, CSPM. So most of these are provided by the different technology vendors like Contra Security, Imperva, Modi Security, AWS itself providing its WAF. Like that, Google is providing something on GCP, and Azure is providing an Azure policy, etc. Okay. Then monitoring for SIEM, threat detection, vulnerability management, incident responses, etc. Again, AWS, each of these cloud players have their own tool sets. So then there is the pager duty, Falco, runtime, Kubernetes security, etc. So key insights per phase, requirements and design is shifting to the left. So techniques are threat modeling, tools we already talked about. Implementation phases and code security. So we again talked about SAST, SCA, etc. Critical checks is SQL injection, Log4j style vulnerability checking. Okay, testing for pre-deployment validations, DAST, IAST, OWASP, ZAP kind of testing. Deployment or infrastructure security, IAC scan, security management, etc. Operational monitoring testing, RASP, WAF. So these are all repetitive concepts that I wanted to highlight once again because they are all very important concepts. Okay. So tool OAuth ZAP is focusing on DAST. SQL map is automated SQL injection exploitation. Sonar Cube for SAST. Checkov is for IAC and for Terraform and called cloud formation. Sync is for SCA plus container scanning. Trivi is for container IAC vulnerability. Okay. So different kinds of defects they are supposed to highlight. Okay. Then there is called as runtime protection, RASP, which we talked earlier. What does RASP stand for? It is runtime application self-protecting. It block attacks in production. Okay, these are all go live on the live production environment related testing. Example, contrast security. Container security scans the Docker images for or the K8 Kubernetes for misconfigurations. Aqua securities, Prisma Cloud, etc. Okay, runtime application self-protection, RASP, is the evolution of SAST, DAST, and IST, but on the production environment. Integrate with the application, analyze the traffic and end user behavior at runtime to prevent attacks. These tools are used after production release, so they are more focused on securing than testing. Okay, this is more of security. So it is actually at the fag end of the 9 years. Okay, so different kind of tool sets available here. IDB protection, RASP, Immunios, there K2 security platforms there. Okay, so Impervita real time is there. Then there is Varatech Enterprises. These tools are very expensive, but they have a critical role to play for runtime protection. Okay, then continuous compliance, codify compliance rules. Okay, using open policy agents. Okay, automate and audit tools like chef for inspect. This is all as part of the continuous compliance. So open policy agent is an open source general purpose policy engine that unifies policy environments for the stack. So it handles the infrastructure, it APIs, microservices, CI/CD pipelines, data systems, etc. So policy as code, decentralized. The features are policy as a code. Just we saw infrastructure as a code. Here we are seeing policy as a code, decentralized enforcement, unified control, and dynamic context. So how this open policy agent works is that there is a service application, there is a query for can user X do Y kind of thing. So then open policy agent evaluates the policy inputs and then provides a decision. So the services and policy queries, okay, evaluation of PHX and output is the returns. So OPA tools ecosystem are gatekeeper tool, Confest is a tool, Citra, DAS, each of them have a purpose. Gatekeeper is for Kubernetes admission controller, Confest is for testing the Terraform, etc., or the YAML configurations. Stira DAS is for enterprise OPA management and policy lifecycle monitoring. OPA Playground is for Rego Playground development and policy prototyping. Okay, in a typical DevSecOps pipeline, Terraform plans JSON contest for OPA, pass or fail, integrate, passes on to the CI pipeline. When it goes to the Kubernetes platform, API servers, admission request, OPA gatekeeper provides allow or deny. Okay, when it comes to microservices, authorization query, OPA provides a sidecar, okay, application denial. So then there is a threat monitoring. Sorry, I'm running faster because of some time crunch. Threat monitoring and responding. Okay, objective security information and event management tools or software solutions that aggregate, analyze, and manage security data from various sources within an organization's IT infrastructure. Okay, then tools like Splunk, ELK stack. So you start analyzing based on the logs. This is basically for log analysis, long-term analytics of based on the logs of different kinds of errors, runtime errors that are documented. Of course, we have as part of the SDLC, you have to capture all these exception handling and log it, which will be later on analyzed and inspected to come up with better tools for proactive reactions. Okay, log management, real-time monitoring, threat detection, incident response, and compliance reporting. Okay, moving on is a high level roadmap, starting with assess, automate, educate, monitor, and iterate. Audit, assess for where we are doing the audit existing for the pipelines for security gaps. As part of the automate phase, integrate the SAT SCA into the system, into the continuous integration and deployment system. Then train the developers on securing coding as part of the OAuth top 10. So you have to, there's a learning curve. You have to educate them in terms of what are the top 10 threats, security threats, and how to mitigate them right from the SSDLC's left shift requirements gathering phase, and monitoring during the runtime using deploy like RASP or SIEM for runtime threats, and the whole process has to iterate. Okay, so the maturity model from a ad hoc to a defined to an integrated to an automated to an optimized stage is where the actual flows. So the more mature is the optimized. Sorry, it should be level 6. I mean, okay. So almost we are in the fag end of the discussion. I missed that. Sorry. Okay, so this has to be level 5. Okay, this is a reference pipeline. Okay, I found it on the internet, very useful to explain. So this is the source code. These are different tool sets. This is the team city. A various tool set as part of the continuous integration doing test and scan. What are the tools here? Okay, what are the different kinds of artifacts management and maintenance? Okay, this is the DevOps pipeline, different tool sets for deployment and monitoring, etc. Okay, so then there is the different phases and different tool sets there. Okay, there are key performance indicators and metrics available. DORA metrics is one of the standards developed by the DevOps Research Assessment, DORA in short. Uh, these four key parameters, they help in they prescribe and help in maintaining good DevSecOps health. So the four parameters mentioned here: development frequency, deployment frequency, how often an organization successfully releases to production. The success rate of deployment is one metric. Okay, lead time for changes, the amount of time it takes to commit to get into production. So once I make a code change, when I commit the source code, what time it takes to go live is another lead time for changes. Okay, how frequently I change and what is the lead time for that change, and the mean time to restore. So how long it takes to restore the services after the incident. So some incident or security threat or a bug or something is there, what is the mean time to restore back to normalcy is another parameter. And change failure rate, so which is called as CFR, is the percentage of deployments on production that results in the degradation of the service and requirement remediation. So how often these failures happen is a rate which also measures the health of the DevSecOps cycle. Okay, then there are security specific KPIs to measure the security dimension of DevSecOps. Organization track metrics that reflect their ability. Okay, mean time to detect, MTTD. The average time it takes to discover a security is a parameter. Vulnerability remediation rate, VRR, is another important thing. Security burn down, a time series chart tracking the number of open, unsolved, resolved security issues over time, and proactive compliance percentage. So these are all some of the parameters and key metrics available for assessing the success or failure of DevOps, DevSecOps pipelines. Okay. So deployment frequency, lead time to change, MTTR, change failure rate, mean time to detect, vulnerability remediation rate, cost per defect, customer satisfaction, CSAT are all the different parameters. Okay, and so this talks about the definition of that, and the how to measure them. For example, deployment frequency is a count of deployments per team per day or week or month. Okay, and what it means is that it is the rate at which a new code is deployed. Okay, how it translate to business value or profitability? Faster time to market. So deployment frequency enable faster time to market. Okay, so lead time for changes means the time for a code commit to its deployment in production. How it is measures the median time for commit to successful production deployment. So what it highlights is the increased efficiency, reduces development costs, and allows for quicker response. So while the first is faster time to market, the second is lower TCO. Mean time to restore is the average time taken to restore from a failure in production. Okay, then change failure rates is for the percentage of deployment failures. Okay, then mean time to detect is for the average time it takes to identify security vulnerability. Okay, the measure as the time from vulnerability introduction to its detection by a scanner or a test. So how does it help? Is that reduced risk window, minimizes the time of an exploitable vulnerability exists in the system, lowering breach probability. Okay, vulnerability remediation rate. Again, this is the speed at which the identification vulnerabilities are actually fixed. Okay, first is how soon you detect it. The second is how soon you fix it. Okay, so I mean MTTD is more on the detection part. The vulnerability remediation is on the remediation part. Then cost per defect or rework is the cost estimates around it. Okay, and security burnout rate is the rate at which the backlog of known security issues is being resolved. So how soon we are cleansing the security related backlogs as part of the SSDLC cycles shift left. How early we are fixing it is what is measured here. Customer satisfaction is the end customer's actual satisfaction. So it brings him an enhanced brand loyalty. Okay, so how do we build good practices of software engineering, which include SSDLC, DevSecOps, and CI/CD/CS pipelines? Is it has to be a collaborative effort wherein there should be a typical leadership role in championing the vision. So a leader should actually drive this. Okay, then there should be enough education enablement for the different stakeholders that we talked about as part of the entire ecosystem. Okay, and then there is fostering collaboration and transport communication. So then once there's a leadership push is there, then they are educated, then the actual collaboration should fall in, cutting across all these layers. Okay, process layers, people layers, etc. And building an empowerment and trust. End of the day, the overall health of the software has to improve, which will help in building the trust of the stakeholders. Okay, particularly the customers. So now we see an integrated process workflow. Sorry, it goes. We are by default is opening my other window. So there is continuous integration impact, automated requirement validation, test suite planning, then continuous deployment impact, deployment target definitions, environment strategy. Both are part of the planning and requirement phase. Okay, the third part is CS impact, security requirements, automation, and threat model. So what I'm trying to project here, CI, CD, and CS in planning phase. Similarly, CI, CD, and CS as part of the design phase. Okay, where as part of the design architecture, test automation, dependencies. Okay, CD is infrastructure as a code design because it is related to deployment and immutable architecture as part of this. and CS security pattern enforcement and policy as code integration as part of the design. Then coming to the implementation, CI is auto build on commit, unit test execution, static analysis as part of the implementation as CI CD. CI CD impact is on artifact versioning, environment provisioning, and CS impact is on SAST secrets detection and SCA analysis. Coming to the testing phase, uh, the CI impact is regression testing automation, build verification. CD impact is canary testing, blue-green deployment. Okay, and CS impact is DAST scanning, IAST scanning, fuzzing, etc. Coming to deployment phase, CI impact is final build validation. CD impact is zero downtime deployment and auto rollback. And CS impact is runtime protection configuration scanning. Okay, coming to the operations, CI impact is hotfix pipeline triggers. CD impact is feature flag management, auto scaling, and CS impact is RAS protection, threat protection, auto patching, etc. Okay. So planning and requirements, automate the requirements as part of CI, part of CD, it is define the deployment, CS is auto checks. Okay, it is basically whatever we discussed. I'm skipping through this. Okay. So I think I would like to stop here. We discuss in detail the software engineering processes and governances around software development life cycle using security, so secure software development life cycle, DevSecOps. Okay, the development team, operations team, and the security team, how they integrate together. And then we talk about CI, CD, and CS pipelines, how the automated or semi-automated pipelines help the continuous integration, continuous deployment, delivery, and continuous security across the SDLC lifecycle. Okay, so these are all the traditional technologies, processes, and methods we talk. How these traditional technologies, processes, and methods are today enhanced in by AI, generative AI, and its agentic partners ecosystem is okay, is what we will be covering as part of the next discussion. Stay tuned. Please share your valuable feedback. It will help tuning it. Sorry for some of the interruptions as part of the thing. I'll see if I can edit it and share it. Okay. Thanks all. Stay tuned. Do subscribe to the channel and share your feedback and likings. Okay. Stay tuned. Shri Gurubhyo Namaha. Thank you. Let's stop the session now.